Hi, today we're going to take a closer look at turning the aircraft. This is something that actually applies pretty much the same whether we're talking about an airplane or a helicopter. There are two things that we can do to increase the performance of our turn. And by increase in performance, what I mean is tighten the radius of the turn. One of the things we can do is increase bank. What that does is it increases the horizontal component of lift, which accelerates us towards the center of the turn. The other thing we can do, in addition or instead of increasing the bank, is that we can decrease our radius. That gives us a tighter turn without increasing the centripetal or inward force. So this is what it looks like when we vector it out. This aircraft is in a 30-degree bank, and its total lift is represented by the orange line. That total lift actually has two relevant components. One is the vertical component, which has to act against weight, and the other is the horizontal component, which accelerates us towards the inside of the turn. We can call that the centripetal force. That's the force that moves us towards the center of the circle. The formula for that we get from our trigonometry basics of SOHCAHTOA, and in this case we're going to use the tangent, which is the tangent of an angle is the opposite over adjacent. So in this case, the angle is here, and so the opposite is this leg, and the adjacent is this one. So the opposite represents the centripetal force, the force that's acting towards the inside of the turn. The vertical one is what acts against the weight. That's sometimes written down as LV for the vertical component of lift, but we can substitute weight there because we know that that component has to be the same as the weight. So we can simplify that by saying, and solve for the centripetal force by saying the tangent of that angle times the weight equals centripetal force. All we've done there is solve for the centripetal force. Now we plug that into our scientific calculator for 30 degrees and the weight of this aircraft. Do the math, and it comes out to 964 pounds of force towards the center of the turn. You can think of this if you kind of picture the aircraft flying by you without banking and somehow lassoing the wingtip to pull it around in a circle with no bank. You would have to pull on that lasso with almost 1,000 pounds of force to get the same radius of turn as a 30-degree bank provides. So let's take a look at that from the standpoint of Newton's second law. When Newton's second law is rewritten to describe how things behave in a circle, it looks like this. The centripetal force, Fc, equals mass times the velocity squared divided by the radius of the turn. So in other words, the mass of the object has an effect, obviously, on how hard you have to push on it. How fast the object is moving also has an effect. Both of those increase the amount of force required. The radius of the turn, on the other hand, the larger the radius, or the bigger the circle you're allowing the object to move in, the smaller the centripetal force is required. So now we can solve that formula for radius rather than the centripetal force, and we can come up with a formula that gives us a radius of turn. So let's play around with turning that into something that we can really use. This is going to get a little bit mathy, but you don't have to be able to do this. You will have to remember some form of the final formula that we have for some of the commercial test questions. So let's take that mass times velocity squared divided by centripetal force. We know that mass equals weight divided by the gravity. Our local gravity here on Earth is 32.2 feet per second squared. And so mass equals W divided by 32.2. So we can replace the mass in our formula here with this formula instead. And that looks like this. This formula is now here and here. Everything else is the same. The velocity squared and the centripetal force are just where they were before. We know that the centripetal force, the formula for that from our last slide, is the tangent of the bank angle times the weight equals the centripetal force. So now we replace the centripetal force with this formula right here, tangent of the bank angle times weight. But look what happened. We have a weight here and a weight here. When that happens in a formula, they cancel out. So what's left is the radius of the turn equals velocity squared divided by 32.2 times the tangent of the bank angle. So let's play around with that formula a little bit here. Now, the velocity has to be converted into feet per second in order to use this formula as is. The reason for that is that the acceleration due to gravity is in feet per second squared. So let's put in 60 knots. We convert that to feet per second. We're going to put in a 30-degree bank angle. And what that gives us is this number divided by this number gives us about 550-foot radius. So at 60 knots at a 30-degree bank, we can get about a 550-foot radius. That means the total circle is going to be double that, about 1,100 feet across, if we fly in a big circle. If we increase our speed to 90 knots and keep the bank the same and do all the math, the radius of turn bumps up clear to 1,237 feet. So increasing from 60 to 90 knots had a very big effect on the radius. In fact, to get the radius back down to what it was before, we're going to have to increase our bank way up to 50 degrees of bank in order to get that down close to what it was before. If instead of using feet per second, we want to use knots and pounds, we have to change those constants just a little bit. It's just a matter of conversion is all it is. But this is the formula that you will often find in the textbooks for flying. And that 11.26 has been converted so that you can use knots on the velocity instead of feet per second. Everything else works the same. You'll also find a formula, especially when you're working on your instrument rating, that gives you rate of turn rather than radius. And you'll see it's very similar. We have this constant here, 1091 times the tangent of bank divided by airspeed in knots. That will give you your rate of turn in degrees per second. So what's this mean to us as pilots? When it comes to radius of turn, our concern here is maneuvering typically for landing or to view something on the ground. And it's important to keep in mind that if you're moving really fast, steep bank angles are going to be required for the same radius of turn that you could get at a much lower bank if you were going slower. So slowing down is a really good option when you're in an airport area or maneuvering towards a landing zone. Increasing bank will also tighten the turn, but you have to be concerned with the accelerated stall in an airplane or some sort of retreating blade stall with the helicopter. The rate of turn becomes a real issue when we're flying on instruments. The bank required to get standard rate, which is 3 degrees of heading change per second, increases with airspeed. So, in other words, the faster you're going, the more bank you need to get standard rate of turn. But we're never supposed to exceed 30 degrees of bank IFR. So when you finally graduate to something where 30 degrees of bank won't get you standard rate, what we'll typically do is go to a half standard rate turn. That makes it predictable as to how long a given amount of turning will take.